Now that you've had an opportunity to work some limit comparison test problems, I want to go ahead and do some more examples. Not really anything strange or different about them, just an idea. Again, the limit comparison test is a pretty powerful test for us, and we can use it quite often. So I just want you to see some more examples worked here. So let's do this first one. If we call this A sub n, and we go on the hunt for a B sub n, then I would say, and hopefully you can see that, for large n, this is acting like 1 over the square root of n squared, because the minus 1 is not playing a role. And the square root of n squared would act like 1 over n. All I have to do is identify it as the harmonic series and state that I know it diverges. And then put these A sub n and B sub n series in a limit. That's going to be n over the square root of n squared minus 1. Now again, this is where I really don't care if you show me every single little iteration here. I'm okay with you taking some shortcuts here. Just as we said, how does this behave for large n? Oh, well, it behaves like 1 over n. We can do the same thing here. We know the minus 1 for large n is not playing a role, so the denominator is acting like this. So the denominator is really just acting like n, and n over n is 1. And that's a good result for us. As long as this result is correct, I'm okay with you not showing every little, step along the way. So I'm perfectly okay with that. I want you to pick up the original series, however, and show that that exhibits the same behavior, and justify it by stating you have all the pieces for the limit comparison test. So again, not a whole lot of work involved here. If this is A sub n, for large n, the numerator is acting like 5n, the denominator is acting like n squared. So for large n, this is acting like 5 over n. Again, I'm going to say it's just acting like 1 over n, because 5 times that is not going to affect convergence or divergence. So again, this is acting a whole lot like the harmonic series, which I have to show the AP reader I recognize that it diverges. Plug these two things in the limit as n approaches infinity. So I have n, which is 1 over n, times 5n minus 3 over n squared minus 2n plus 5. I would go ahead and do one more step just for myself, if nothing else, to clean up what's happening here. For large n, these things right here are not playing a role. For large n, this is acting like 5. So the original series, and don't come over here and say A sub n, because if you don't have it clearly written somewhere on your paper that that is equal to A sub n, to come down here and say, well, okay, well then A sub n diverges as well, this has no meaning unless you have stated clearly somewhere else in your work that that is A sub n. So it's my opinion, I would much rather see you just rewrite the original series. You've always got time to do that. So that is n squared minus 2n plus 5 diverges by the limit comparison test. All right, so there we go. So let's work another example here. This one looks a little more complicated. Let's see if we can find a B sub n, how this might behave for large n. For large n, the plus 1 here on the bottom is really not playing a significant role. Let's just come out of here and I'll mess around with it here. I want you to notice that if I multiply the same bases, I add the exponents. So the 2 to the quantity n minus 1 is really behaving like so. I could even say that 1 over 2 to the negative 1 is 2. So it's acting, really it's acting like that. 1 is 2 times n, and the 1 in the bottom is 2 to the n. For large n, it's not really having any effect there. So for large n, this is pretty much acting like 2n over n times 2 to the n. Algebraically, those disappear. And I could go back, even though I put that in the numerator. I could say that, but frankly, I did that because you can see that this is just a constant. And remember, if we have anything multiplied, any constant value multiplied by the meat of our nth term, that has zero effect on convergence and divergence. So frankly, at some point, I would like for you to be able to look at that and say, you know what? N over n plus 1 for large n is just acting like 1. And 1 over 2 to the n minus 1, or 1 over 2 to the n times 2 to the negative 1, that 2 to the negative 1 is playing no significant role as n gets larger and larger and larger. And the more you work with these, the more you'll be able to do that a lot quicker. So frankly, that's a good B sub n. This is a geometric series. I would show the absolute value of r is 1/2, which is less than 1. For a geometric series, I know that converges. So I would say the limit as n approaches infinity, 2 to the n times n. I've taken b sub n and flipped it and am multiplying straight across. N plus 1, 2 to the quantity n minus 1. So again, for large n, that's acting like 1. For large n here, and this might be something that I would go ahead and do. I think we saw a while ago why I can say it's behaving like that. Algebraically, that's acting like 1. That's a good result here. So the original series of n over the quantity n plus 1 times 2 to the quantity n minus 1 converges by the limit comparison test. So even though I'm letting you take some shortcuts when it comes to evaluating the limit and not showing every little step of L'Hopital's along the way, there's still a lot of algebra here that you're going to have to get comfortable with and that you're going to have to get really confident in. And so until you're super confident, I want you to go ahead and show all those steps. So here, let's see how this thing is behaving for large n. So let's say for large n, it's really behaving kind of sort of like that. Would you agree with that? So for large n, it's kind of sort of behaving like so. Or we might even say like so. N plus n would be 2n. So I would be tempted to use the harmonic series. Again, I guess we could just go ahead and say the harmonic series as b sub n. I would want to say that that would be a good choice for b sub n. All right. So let's put that inside the limit. As n approaches infinity, 1 times n is n. If I flip the harmonic series and multiply straight across. So I would say that for large n, that this would, again, the denominator, just as I did in picking large n, here, the denominator is pretty much acting like 1 over 2n. So the numerator's acting like n, the denominator's acting like 2n. So I would say that that's 1/2, and that's a good result. So the original series, n equal 1 to infinity, of 1 over n plus the square root of the quantity n squared plus 1 diverges by the limit comparison test. You can see how important this step is. If you make a mistake and say that 1 over n plus n is acting like 1 over n squared, then you're going to compare this with a p-series that converges. So your choice of b sub n is super, super, super important. So make sure you become very, very good at that. Again, we're only concerned with what's happening for large n. For large n, this is acting like n over n to the 4th. So I would say 1 over n cubed would be a good comparison. This is a p-series. See how important it is that we recognize geometric series and p-series and the harmonic series. This is a p-series where p is 3, which is greater than 1. This series converges. So let's plop those in the limit. As n approaches infinity, that's n cubed times n over, let's go ahead and expand this. That's n to the 4th plus 2n squared plus 1. So we have n to the 4th and n to the 4th that are the leaders in the numerator and the denominator. That's acting like 1. That's a good result for us. So the original series, n over the quantity n squared plus 1 squared, converges by the limit comparison test. So hopefully you see that it's just getting more and more and more kind of repetitive on what we're doing here. So b sub n for large n, this is acting like 1 over 4n squared. So I would say 1 over n squared, because the 1/4 can be factored out front, and it has absolutely no effect on convergence or divergence. P-series where, it's a 1, where p equals 2, which is greater than 1, this one also converges. And you can see making really good choices for b sub n will almost always result in you getting a real number value out of this limit. And that's really what you're after. We haven't in any of these examples, because we've made such great choices for b sub n, we haven't had to, compare with infinity or with 0. We've forced this to almost always be some real number value, because we've made such intelligent choices for, we're going to say that acts like 4n squared for large n, even though I know it doesn't really expand exactly that way. I guess for argument's sake, we ought to go ahead and just do that. So this is acting like 1/4. So a sub n, our original series, does it matter that it starts at 3 instead of 1? No, because where does convergence happen? Convergence happens and divergence happens for large n. So this converges by the limit comparison test. So hopefully seeing that over and over and over will help you make some good choices for b sub n. All right, so we don't have to show near as much work as it originally looked like we were going to have to. The biggest thing that I would say is this is the kicker. Without that, you don't have a good justification for limit comparison test. Come to class next time. We'll work some more homework problems.